my joy comes out of being crazy, not out of being sensible. And for that one, I've got ideas on how to theoretically consistently build time travel into quantum computers. Practically, there are ways to test this. I have ideas, but the idea is to incorporate time travel. And I think I can prove that if time travel is built into a quantum computer, a quantum computer could be really good if we find problems that have a structure that's amenable to where the advantage of quantum computing comes up. So where's the future of quantum computing? Well,
thank you for joining Once Changing the World, India's first Future Tech Meets Sustainability podcast. And today, I'm delighted and honored to have with me Professor Barry Sanders. He is the Scientific Director of Calgary's Quantum City, tasked with building a quantum innovation ecosystem. Professor Barry's theoretical research includes quantum sensing and metrology, quantum and quantum resilient communication, quantum computing, and quantum optics. He held numerous distinguished international visiting professorships and affiliations globally, and is a scientist with the Creative Destruction Lab. Professor Sanders is the chair of the board for Deep Tech Canada, an affiliate of the Perimeter Institute for Theoretical Physics, a scientific board member for the Open Quantum Institute and for the Google X Prize in Quantum Computing, and undertakes outreach in the developing world, including teaching and training in Africa, Central Asia, and South America. Sanders is the co-lead of the International Research Network Canada-France Quantum Alliance and serves on numerous expert panels in Canada, the USA, and the European Union, plus several European countries, and is on standards committee for both quantum and nanotech. He received the City of Calgary International Achievement Award in 2022. So, Professor, really appreciate taking time being part of the podcast. It will be great if you can start with explaining what is a classical computer versus a quantum computer, and how does a quantum computer differ from a classical computer?
Sure, yeah, that's exactly the right way to begin. What's a computer, and then what does a quantum computer add to it? And so a computer is a machine, and the machine accepts inputs that are zeros and ones, and the output is zeros and ones. And then what the machine does is it performs some kind of logic operations to convert the input to the output. And the output could be a Word document. It could be the solution to a optimization problem. It could be, the trajectory that needs to be followed for a rocket to land at the right place on the moon. So computers are able to do that. The machinery inside is based on what's called Boolean logic. And so in Boolean logic, you're performing arithmetic on the zeros and ones. And then the arithmetic has operations like NOT that convert 0 to 1 and 1 to 0. And then there can be AND gates, OR gates, NOT gates, and we can build up the logic from there. And so essentially what a computer does, it's programmed to apply certain logical operations to zeros and ones to yield the desired output. Now let's go to a quantum computer. So a quantum computer also accepts zeros and ones on the input and yields the answer. So anything you would do with a quantum computer, you can do with a non-quantum computer, and we call that classical. So we quantum scientists use the word classical to refer to anything we don't think is quantum. So the quantum part is inside the machine. If you're a user of a computer, you don't really care if it's quantum or not. It's just, will the quantum computer be better in some ways? And the answer is, it's better in some ways. It does work. Now, let me draw a distinction here. So there's a whole area of nanotechnology, and even going finer than nanotechnology. And the idea there is to make transistors and chips smaller and smaller, and then try to get more speed, maybe less heating. And so in the nanotechnology areas, they make better computers. The idea is to pack more transistors on a chip and to get more computational power. So nanotechnology, one of the applications is to make computers better and better for every problem you would run. Quantum computing is different. In quantum computing, we employ a different logic. So instead of this Boolean logic, NOT gates, AND gates, OR gates, we accept the input, and then I can explain more, but essentially we convert the input of zeros and ones into some quantum version of that. Then we do our quantum logical processing, and then we convert back to a classical output. And by changing the very fundamentals where zeros and ones can be somehow in superposition, and the processing is done with quantum logic, makes some problems So it's not about speeding things up. It takes certain problems and makes them, instead of being hard, being easy. And then I know I'm talking too much, but I'll just finish it off by saying a good example of hard is the following, that when we encrypt on the internet, so if we use HTTPS instead of HTTP, that S on top gives us a transport layer security that will ensure that what we send is encrypted and not breakable. But it's breakable. What makes it unbreakable is beliefs about making the encryption a little better makes the ability to crack it exponentially harder. So that's the foundation of the belief. But with quantum computers, at scale, we can break these kinds of encryption in an efficient way. Basically, it's no longer exponentially expensive. So we have efficient ways to scale up. And then that's where quantum computers come in. There are a few problems where a quantum computer changes the paradigm of hard to easy, not like nanotech where it makes everything faster.
Right. Professor, I really, really appreciate you explaining and breaking down the difference between a classical computer versus a quantum computer. A classical computer works with Boolean logic, uses binary code, yes and no, zeros and ones, while a quantum computer uses superpositions, zeros and ones, ones and zeros, and that's what gives it the quantum advantage, basically, in a certain spaces. It also leverages entanglement. It'll be great if you could, elaborate this, superposition and entanglement. How does that give it advantage in certain cases, like you mentioned?
Sure. So I think I'll illustrate it with the famous example of Schrödinger's cat. So Erwin Schrödinger, an Austrian scientist, is one of the pioneers of quantum mechanics. So 100 years ago, he was a major player in developing quantum mechanics. And then he illustrated the paradox of quantum mechanics, the superposition, by imagining a case where a cat is put inside of an opaque box, so you can't see how the cat's doing, and then put in a radioactive nucleus. And then people might know, with radioactive nuclei, you use a Geiger counter, click, 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 they're picking up radioactive decay. So somehow you think of this nucleus, when it decays, when the decay is detected, it triggers a poison gas that kills the cat. But in quantum mechanics, it's not like the nucleus decayed or didn't decay. In some sense, it's the Geiger counter clicking that makes that decay real. So with a nuclear decay, at the same time, there's a reality or a description where the nucleus hasn't decayed and it has decayed. And then the idea that Schrödinger pointed out is the logical consequence of that is that there's an entanglement between the nuclear decay and the cat state. And the upshot of it is that if quantum mechanics is right, even the idea of life and death becomes philosophically problematic, because even life and death are no longer very distinct possibilities. You can start imagining a superposition of life and death. On an easier level, you can imagine an electron. An electron spins. So electron's a point particle, but in some sense we say it spins. And when it spins, it can be spinning one way or the other. If it spins this way, the axis of the spin is like the Earth. The North Pole is the North Pole geographically because of the spin of the Earth. If the Earth spun the other way, the North Pole would point down. And we do have discussions about whether at least the magnetic north could flip. The Earth could have a flip. In a quantum world, the Earth could be in a superposition of spinning one way and spinning the other. And so what does that mean? It's not probabilistic. It's not saying both exist at the same time in different realities, but rather it becomes like waves. And so if you imagine you're in a room with other people talking, you're talking to somebody, other people are talking. The sound waves that go from your mouth to the other person's ear go through the air, compression waves. And somebody else talking will have these compression waves that will go to the other person's ear. And you can hear the conversation you're having. There's no distortion of the sound waves by having other transmissions. Things can exist in superposition. So you can have the sound waves, just whatever the sound waves are going from me to you, and somebody else is talking, they just superpose into collective bigger or smaller compressions. Or if you think of water waves, if I throw a stone in the water and then it creates outwardly moving circular waves, and you throw a stone in the water somewhere else, the circular waves grow and they cross each other. And so there could be a superposition of those waves. And so in quantum mechanics, the essence of it is that there's this duality between what we call particles and what we call waves. And in a quantum computer, in a sense, we're taking zeros and ones, which I think of as having a particle property. Then we convert those in the way I interpret into some kind of waves. Then we do our logic on the waves, and then we convert back. And if we're lucky, for certain problems, the wave-like part of the processing has an interference effect that cancels out. And if you can make part of your computation cancel, it's like you got that part of the computation for free. It all sounds weird and magical, but what I'm saying is defendable against an expert. I'm confident in what I'm saying.
I think the quantum world is doing something which I think still remains in, I don't know, maybe if I'm using the right term, the woo-woo zone, because of its paradox of, the wave particle duality. Maybe you can elaborate on that. Another thing, something that I wanted to touch on is Geordie Rose, ex-D-Wave from Canada, and then David Deutsch. They both claim that quantum computers operate by tapping into parallel universes, which supports the many-world quantum interpretation. And then Hartmut Nevin from Google Quantum AI also recently claimed that their Willow chip speed suggests that computation, the computation happens in the parallel universe. So will be great if you could, share your thoughts on the many world quantum interpretation, and do quantum computing actually tap into these alternate parallel universes for its compute?
Okay, so you've asked me two questions. The first one is the measurement paradox, and the second one is the many worlds, which attempts to circumvent the measurement paradox. So let me answer the first question first. And so the first question was, there's a big philosophical problem. And so we understand, we think that the whole universe is described by quantum mechanics, which means we should be able to describe everything that happens in the universe according to quantum mechanical principles. But then we have a philosophical belief that science is about facts, and facts arise out of observations, measurement. So we need to be able to perform empirical observations to be able to collect facts that we use to develop a theory. The problem is, how do we observe? So we see, we hear, but all of these ways that we observe or measure what's around us should ultimately be described by quantum mechanics. As I said, like the Schrodinger's cat can be an alive and dead. So in some sense, everything that we see, it's all possibilities in superposition, and that's not reconcilable with the way that the philosophical foundations of science. So metaphysically, we need to have observations. So that's the measurement paradox. And then a lot of interpretations of quantum mechanics arise to try to get around that problem. And there's various ways to do it, and all but one come down to either accepting there's a paradox or trying to say that on some large enough scale, quantum mechanics dies out. That somehow, if we don't try to think of measurement at the very small scale, then we could try to circumvent it. And these are all problematic. We don't have a solution to the philosophical conundrum. The exception to this is the many worlds interpretation. Hugh Everett III wrote a paper in the late 1950s about it. And so this is the idea where you say, and remember what I said about the cat and the nuclear decay. So you say, well, the cat is alive if the nucleus didn't decay, cat's dead if the nucleus did decay. And then what you do is you decompose your quantum description in these relationships, and then you say, well, it's not that the cat is alive or dead, or it isn't, but rather that possibility of a nuclear decay means that we split the universe into two. So there's a universe where the nucleus decayed and the cat's dead, and another universe where the nucleus didn't decay and the cat's alive. And so all the evolution of a quantum system results in a proliferation of these universes. And you get this multiverse interpretation. It's mathematically consistent. Physically, it's bothersome. We're not worried about multiple universes in that, but it's kind of like, doesn't it take energy to do that? Where does the energy come from? So on some mechanistic level, it's troubling, but mathematically, it's a consistent way of doing things. And this is actually underpins, there's a research that goes on in consistent histories, attempts to try to explain cosmology, the evolution of the universe accordingly. So now, David Deutsch wrote the foundational paper on how to build a quantum computer, Proceedings of the Royal Society of London A. That was out, I think, 1985, plus or minus a year. And David Deutsch wrote that paper. And I was a student back then, so I remember when the paper came out. And it goes through this whole beautiful approach with how one would build a quantum computer as an analog to a Turing machine. And in the end, like Turing did all the theory, and then in the end, he actually worked towards building a machine. That machine didn't turn out to be practical. But Deutsch is saying, well, let's take Turing's machine and build a quantum version of it. Very beautiful work. And then at the end, he makes an argument along the lines that says that ultimately measurement is about consciousness, and that if we built a quantum computer that became sophisticated enough to become conscious, it would then collapse wave functions. So it would be through consciousness, that's the ultimate form of measurement, is roughly the argument. And then, but if it doesn't happen, if there's not this collapse into some particular reality, then that would justify the many worlds interpretation. So he saw the quantum computer as a pathway to testing many worlds interpretation. Like all interpretations are regarded as equally viable to explain the physics, but he's proposing a quantum computer as a way to really empirically distinguish. And then this thinking lives on as an undercurrent in the area of quantum computing. I don't know what Geordie Rose had said, but I certainly know Hartmut Neven when in the blog related to the Google's Willow chip came out, that Hartmut is talking about the many worlds approach. And so now for me personally, I'm still on the fence because, like the consciousness idea goes back to Wolfgang Pauli, and there are people who work on that. Where does quantum mechanics end and the classical world begins? How do you resolve the measurement paradox? But it's not, I don't understand consciousness at all. So unless I can write down a theory of consciousness and connect it with quantum mechanics, I'm too cautious a scientist to say that kind of thing. But there are braver people than I who posit that quantum computers could justify the many worlds.
Thank you, Professor, for explaining that. Will you be able to also explain what are the different types of quantum computing architecture which are being developed currently, and which approach, according to you, might get us to error-free, fault-tolerant quantum computer?
Yeah, okay. So you mentioned Geordie Rose and D-Wave. So they do, the D-Wave computer originally was targeting adiabatic quantum computing, which is an approach to quantum computing. Very difficult to implement, and there's some theoretical challenges, but they pivoted towards doing quantum annealing. And so I'll just say it's a quantum version of simulated annealing, which is an approach to global optimization. The point relevant to this conversation is that the D-Wave computer and the quantum annealing is purpose-built. It's saying we're not building a programmable quantum computer for any purpose, but we're building a quantum machine that will execute a quantum version of the simulated annealing meta-heuristic approach to optimization. On the other hand, if you take various companies, IBM is probably a very good example. They have ambassadors out there and promote their Qiskit software library as an access point to use quantum computers. They're working towards universal computing. So anything, it can program any quantum algorithm, whether it's useful or not. It's a way of making a programmable computer that can do any quantum algorithm in a way that's efficient, right? You can always simulate a quantum algorithm on a classical computer and it's inefficient, but it can efficiently undertake any quantum algorithm. And so it's a very different approach. Then if you then consider Google's chip and surface code approach, it's meant to be universal programmable. Very different way of operating. Psi-quantum with its photonic-based quantum computing would also be programmable, but a very different kind of operation. So the first thing you're asking about is, like the architecture. Well, first of all, it's the kind of problem, right? D-Wave pioneered building a quantum machine that solves a particular kind of problem. IBM and many of the others are building quantum computers that are programmable, that if you came along with a new quantum algorithm, you could program it into the machine. Now, you asked about architecture, and even the word architecture becomes interesting. There's what quantum physicists building quantum computers call architecture, and then there's architecture that computer engineers would refer to. And they're not the same thing. So in physics land, the word architecture is often used to describe a particular implementation. So, am I building my quantum computer with trapped ions, with superconducting circuits, with photons, with neutral atoms, and so on? And then in the physics land, it's, how do we go down to control at the very foundational level these particular operations in this physical realization? But in the computer engineering world, we have a stack of, it's kind of like there's a stack of different layers, some physical layer, but then you want to be able to have a arithmetic logic unit, a control unit, memory, input and output, all this kind of stuff. And what you'd like to do in the engineering world is say, there's an architecture that I'm going to work on, and it's independent of the physical implementation. It's the job then of, having the architecture, then, you work through the architecture, you work your way to a point where you say, I want this or that gate. And then at some layer, there's a compilation of the program to try to work well in the physical language. There's ways of knowing which quantum bits are better than others. And so you want all that to be hidden. Okay, so in physics land, everything's glomped together in saying, architecture is about making this machine I built work. In the computer engineering world, it's about, should the architecture be what von Neumann proposed? So we talked about the Turing machine. And then the Turing machine, because this infinite tape runs through, you have to, getting your memory is very difficult. So we have random access memory, unit cost per query. And so we have a von Neumann architecture that roughly informs us how to work. And so in computer engineering world, this is still a challenge, is how we design our quantum computer so that architecturally it's sound and has a way of being able to control, correct errors, work its way down to the physical layer. So back to you, I'm just saying that there's two very different notions of architecture.
Thank you for explaining that, Professor. Wanted to get your thoughts on this breakthrough that we're talking about in 2025. Microsoft's Majorana 1, and which is leveraging a new form of matter itself. The fermion Majorana. Will be great if you could explain this Majorana 1 8-qubit topological superconductor and what this breakthrough would mean, along with Microsoft vision to build, scale it up to a 1 million qubit quantum computer. What would that kind of mean? 1 million quantum computer with this new form of matter itself to the world. What would be great if you could talk about that.
Yeah, so we talked about different implementations: ion traps, superconducting circuits, neutral atoms, photons are examples. And then what Microsoft is betting the bank on is a form of quantum computing, has a superconductor semiconductor interface. And the idea is that so let me try to put it this way. So with the electron spin up or down, spin up or down could be 0 and 1. And then if the electron spins in some other orientation, that could be a superposition of 0 and 1. There's the photon, and it can be encoded in the polarization of the photon or something. The idea is that the quantum information is local somehow to a particle, an atom, an ion, etc. And then errors happen, that there's interaction of an ion with the ion trap around it, the photon can get lost. And so we have our error models, and we have the idea that quantum information is associated with a particle. On the other hand, with the Microsoft direction, you say, no, instead of that, it's associated with some topological encoding. So imagine like a string, and then if you made a string into a loop, and then if you the string has certain properties, the length of the string, and if you deform it from being a circle to some other shape, the length doesn't change. So I'm oversimplifying a lot, but the idea is that instead of encoding into a particular particle, you make a quasi-particle. And the Majorana, theoretically, it's fundamental, but what Microsoft's building is it's called a quasi-particle. It's effectively a particle. It's quasi-particle. But the idea is that somehow it's more resilient against errors because deforming it, damaging it in some way, as long as the properties are encoded topologically, it's safe. Just to give you a famous example of topology. So topologists are often said to be mathematicians who can't tell the difference between a donut and a coffee cup, because a donut has a hole in it. A coffee cup has, I got one. Yeah, here. So the coffee cup has a hole here. And if you can continuously deform the coffee cup into a donut, then they're equivalent topologically. And then if you protect against that, you say, well, errors are going to occur on deformations, but everything I do is under an equivalence of any deformation that preserves the topology is safe. So that's the idea. It's really hard to do. And Microsoft has had a bumpy road along the way. So along the way, Microsoft, unfortunately, has had to even have retracted papers when they've made certain claims. Microsoft's a very honest organization. So, I'm not attributing to them any deception. That it does happen in science that sometimes claims do have to be retracted. But it did, there were road bumps. And then Majorana is justifiably proud on getting to where it did with one qubit. But they have one qubit at the moment, and they need to still show a full set of operations. The reason that they do this is, and you mentioned before, like we're getting on this road to fault tolerance and error correction. So what happens now is when you use a quantum computer today, they don't correct the noise. So as you get a deeper and deeper logical circuit, the more operations, there's this exponential overhead of errors. And, if quantum computers are going to be exponentially better, and yet there's an exponential overhead of errors, we kind of lost the advantage. So we need to get to the point where we're correcting errors as we go. And then the Microsoft hope is that by using topological quantum computing, then the error correction overhead drops. So they're hoping that by using their topological form of quantum computing, they can somehow, like right now they have only one qubit, but they can speed ahead because while the rest of the physical implementations are trying to correct errors, Microsoft can get around it. There's one terrible issue that we have to contend with. So it turns out if a topological system is very resistant to getting errors, if an error occurs, it's very resistant to fixing it. So this is always something to watch, that if an error is rare to happen, it's equally hard to remove. Now, maybe they have a way around it, but that's a red flag on that.
Canada has been leading in the quantum technology space. Geordie Rose's D-Wave was one of the first quantum computing company which kind of built as well as shipped these quantum computers. Don't really know whether they are like completely practical, but yes, they were the first in lines. Can you talk about Calgary's quantum city, and what can other nations and institutes learn from your effort in building and empowering a quantum ecosystem?
Yeah, well, first of all, quantum computing is really hard. And so success in quantum computing requires a global effort. And a global effort is actually really difficult now because quantum computers, rightly or wrongly, is seen as a potentially threatening technology, And so more and more things like export controls and restrictions are coming down to limit that amount of international collaboration. And this is unfortunate from my point of view because the more we can work together globally, the quicker and better we'll make these quantum computers effective. But it is what it is. Who might argue with people who claim security considerations override, but they do acknowledge that it slows things down. Then you said about Canada being in the lead. And so the reality is that to be in the lead, you need a lot of funding going into this. And so the US has really good, both companies like IBM, Google, Amazon Web Service, Microsoft, big companies working on this. And then at the same time, and NVIDIA is getting involved in certain ways. And then there's also the startup companies in the US, IonQ, Quantinuum, et cetera, PsiQuantum. So it's very hard to keep up if you're in a smaller country than the US. On the other hand, there are ways to collaborate. So in Canada, as you mentioned, D-Wave, Canada's got another scale up. It's Xanadu. So Xanadu is a quantum computing company in Toronto. They've raised a good amount of money. So they're building up. There's also Photonic in Vancouver, which is a semiconductor-based quantum computing effort. So Canada has been doing well in developing the companies, but whether Canada is big enough and strong enough on its own to be able to carry quantum computers to ultimate, commercialization and widespread use is less than clear. Like my own view is that, we'll need to find ways to collaborate. Even the US is not big enough to be able to carry these things on to the ultimate success. I'm one of my roles, half my job is scientific director of Quantum City, and then Quantum City is a initiative in Calgary. It's funded by the province of Alberta, funded by the University of Calgary, and also partners with Emphasis. So Emphasis is India's 8th largest IT company, and it's Blackstone backed, so it's got deep pockets. And Emphasis, which has a strong link with IIT Madras and also Ashoka University, and then Calgary is like another partner in that. And the quantum computing headquarters for Emphasis is in Calgary. And so we work, so through that three-way partnership, University of Calgary, Province of Alberta, and Emphasis, we've created this quantum innovation ecosystem. And then what makes us, like most of the quantum innovation ecosystems work as follows. You say, like if I'm a quantum scientist, I say, give me lots of money and I'll invent really cool things and they'll work and the world will come to buy them. Everything will happen. And that's not my perspective. It's not enough to go out and invent cool things. You have to do the customer discovery. Who's going to use it? How are they going to use it? What are the steps along the way? How do you standardize? How do you build up a venture capital base? Do you run accelerators and incubators? So there's a lot of pieces that need to come together to make a quantum innovation ecosystem that goes from the science and technology to the innovation itself. And then the innovation is about creating products, maybe creating services. And so that's what we're doing. And then in our vision in Quantum City is where quantum technology becomes quantum solutions. So what we're building up is we have excellent quantum science and technology. We're not trying to cover all bases, but we're trying to be the funnel where if somebody in the world invents something, good quantum technology, and somebody in the world needs quantum technology, they might not know it, we're the world experts on how to match the solution to the problem. Quantum technology is solutions in search of a problem, and people have problems and they're searching for solutions. And then my dream is that, they'll say, how do I make use of it? I better go to Calgary and ask Quantum City. So that's where we're heading is we're hoping to be the global leaders in that funnel between one and the other.
Right, Professor, wish you and the entire team the very best. And I hope that the world kind of understand that we're sitting at such a fantastic point of time. These technologies in the next few years are going to completely augment humanity. And maybe we'll truly understand who we are and what our role is, because yes, I mean, maybe you kind of pointed out or hinted towards, what's happening with the current global race of sorts, where I think nations are trying to acquire these exponential tech stacks such as AI or quantum computing. And in this race, maybe I think we might just possibly trigger a global war of sorts, because US has already just recently created this AI diffusion export policy and along with Nvidia, they've kind of divided the entire world in three different camps. The ones who are the allies, and the second was maybe some support, and the third is like completely banned, like the China, the Russia, and many other countries. I think we are sitting in such a fantastic point of time with these tech stack, which can truly maybe augment humanity to maybe understanding who we are. And I think the only way forward is collaborative rather than conflict. But the way I think way we are going towards is largely what, at least from my perspective, is towards a place which is conflict. And you pointed out that to create a quantum ecosystem you need so much more rather than just maybe create. You need to create a complete sustainable thriving ecosystem with maybe accelerators, incubator, customer discovery, standardization, so on and so forth. India is doing a lot over here, and recently, I think the India government has allocated somewhere around 600 crores for the national quantum mission, and then all of the IITs are like push driving the conversation of the like pushing the quantum industry forward. Do you see any opportunities where you see Quantum City as well as India? The institutes could collaborate and push the ecosystem forward globally, where it works for everyone.
Yeah, well, first I'll mention that talent from India is vital in AI, in quantum, et cetera. And you can look at, even leadership of some of the US companies are people who've come from India. So India globally is regarded as one of the best supplies of talent. And then that's a little bit of a shame too, because, India is producing this incredible talent. Why not, keep people too, to have a lot of the innovations take place within India. So India is in a very special situation. Excellent education system, very smart people, but they feel the opportunity is better if they leave, and there's probably a lot of reasons for it. Is there an opportunity for collaboration? Well, so I was in the first batch of what was called the Vajra scheme, which is the visiting adjunct research award, something like that. So it was a way of bringing foreigners, including but not restricted to people of Indian origin, into India. So I had a few years position at the Raman Research Institute in Bangalore as a Vajra visiting faculty member. And so I do have my own personal experience, a few years of working to collaborate. And we, so I worked in Urvashi Sinha's group, and we worked towards, she's one of the very involved people in the National Quantum Strategy for India. And we did do various collaborations, and we worked together, and I sent people to Raman Research Institute. She had people who come over to Calgary. So it's kind of this personal connection that really matters. So the opportunity is there. It's important on both sides. So I can tell you from my experience, like in Canada, if I go and I say, we need ways to work better with India, and working between Canada and India is like, a lot of people think that working means people from India come and visit Canada to learn stuff, but it's not the way to collaborate. You need both way flow. And so you say, okay, we'll do both way flow, but then the flow into Canada is difficult. I don't experience it. I'm Canadian, but I can tell you when I went to India, they changed visas. So like I'm trying to get into the country and get my visa, and they deleted the visiting professor visa, and then I had to get student visas. And then I go into India, to Bangalore airport, and I show my passport and that, and I'm on a student visa. Say, well, you're too old to be a student. And then I'm fumbling. I'm saying, well, this is I carry all these documents to say, I'm sorry, it's not my choice, but, the government decided a visiting professor comes under a student visa, because they're not going to let me in. And it was just thing after thing. And so what was going on is it becomes really important to make the collaboration that at some policy level and some execution level, it's prioritized. So my own experience is I'm thinking, how can I set up collaborations where it's a two-way added value? We're bringing talent to India. We're not just coming to take people away, but we're building up things together. I did have time in China. So I was also a 1,000 Talent Chair China for a while. And then that's got, the interpretation of that chair now is very mixed. But when I would go to China, I had this R visa. I'd go in. It was like everything I did, I was like some kind of star of a movie star or whatever. Like it was very easy going around doing things. In India, it was more difficult. And so, if we just weigh up the two approaches, in China, the idea is we need foreigners to come in to be able to enrich what we're doing. We'll set everything up so a foreigner has an easy time getting in, et cetera. I didn't find it with India, and I'm not here to criticize the Indian government. 99% of the stuff is great, the hospitality, the way I was taken care of and that. But I'm just saying, when you try to set up collaborations, you try to set up visas, you try to set up ways to collaborate, and that difficulty. We were trying to set stuff up, and then, as you know, I'm sure that Canada and India had a falling out not too long ago, and then it jeopardized the way the visas work. So if we can work together to share the value and set it up so it's easy to get the joint funding, it's easy for the flow back and forth, and it's important for the people who leave India too, because a lot of people leave and then they want to go back. And this is vital, certainly where China started to capitalize on it, and a lot of other countries did this. And you can look after, you can look at various times, different countries that built up. Talent go out, talent come back, and so that's the case. So the short message I have is, I'm not the only one. We want ways to work together. We see the value, but we need to make things easier to be able to work together, and that to me is really the obstacle.
I completely double you, and I'm so very sorry for the inconvenience, but I hope that the listeners, the government, the policymakers understand and realize that, China is doing so cool with this R visa that you mentioned. We need to create an open ecosystem. I think the world is going inwards. Governments are, we live in a hyper-connected world, and what is needed today is to be open and collaborate rather than going inwards. So I hope that the listeners, whoever is listening from the government, kind of take cognizant of the fact that the only way to collaborate is two ways, where it's both ways rather than one ways. So Professor, you've been mentoring quite a lot of startups, with the Creative Destruction Lab, and you also, I think, wrote paper on setting up a quantum computing startup. It's very, very challenging. Maybe you can talk about that, and what's the boldest startup idea that you've kind of mentored, a quantum computing startup that you mentored at Creative Destruction Lab and Quantum City?
Yeah, okay. So probably 6 or 7 years now, I've been a volunteer. So it's strictly a volunteer role with the Creative Destruction Lab. That was founded by Ajay Agrawal at the University of Toronto. So it's a kind of accelerator-like. It's an objective-setting organization. It's got elements of Shark Tank type of, startup people are in front of venture capitalists and angel investors and so on. But it's a nurturing environment. So what we do is we accept in the Creative Destruction Lab, and now it's got branches in different parts of the world. It's a very successful model. Except normally the input should be seed stage companies, and the goal is to massively scale them up. So the dream is that some of the companies entering become unicorns, so get $1 billion valuation. That's the idea. And then I serve on the quantum stream at the University of Toronto. And then I also serve on what the prime stream in Calgary, the Rockies branch of Creative Destruction Lab, and the prime stream is a catch-all. So I kind of do the quantum stream, so I'm well-versed in where startups are in the quantum world, and the prime stream helps me calibrate against a range of other startups. So I understand what usual startups are about. The quantum stream is a little bit different from most streams in the Creative Destruction Lab because they operate under this emerging dual-use technology paradigm. So quantum computing, it has enough potential value, it's worth starting a company well before you even know how the product is going to work, which is different from most startups. And so in my role and the role of other mentors, we take them in and then we make sure that they understand, like, how do you assess where your science and technology is? How do you navigate the risks in development? And risks include geopolitical now, because if you develop something and there's all these export controls, how do you, business, you want to sell to everybody in the world. And these restrictions become an element of geopolitical risk. How do you, what money do you raise? How do you make sure that you're raising from the right places so it doesn't handicap you down the road? How are you thinking about success? Is it an exit by selling to another company? Is it an merger and acquisition model? Is it are you going to grow to a unicorn stage? And then things like there's a lot of government money around. It says so. A lot of companies survive by doing contract work with the government. The government says, "Okay, build something useless, but it's a milestone towards a valuable quantum technology, and we'll pay you for it." And so companies will, like, they have the dream, their vision of what they want to be, but they have to survive by taking money that can distract them from the vision. And so that's another part of mentoring. How do you decide? There's plenty of money out there to make a business. How do you decide what to take and what not to take? How do you decide what you're going to build in-house versus having a grander vision and acquiring or partnering with other firms? How do you, if you're going to make quantum, if you look at the supply chain, how much of the supply chain can live where you have a company that delivers in the supply chain versus how much big companies building quantum computers require things to be secret and would rather acquire the company than have it in the supply chain. So there's a lot of these kinds of questions that come up. And then, as I said, I do it as a volunteer. I help out companies. Occasionally, I wind up also joining the board later on. So, once in a while, some company says, "Gee, Barry, you said something useful, so we'll bring you on board." It happens very rarely. So I don't know how useful I am if more don't bring me on, but that's the situation. And then you asked me what would be the most, you didn't say audacious, but that's the way I think about it. Before I started, Xanadu in Toronto that I mentioned was a CDL startup. And between Christian Wiedbrook, who's the CEO, was telling me once he had another startup that didn't make it. And he was telling me, it's the second one. And often it's your second one that works. And, he was accepting a lot of advice, what they call what venture capitalists like to call coachable. And so Xanadu, in my understanding, before I was a mentor, is an example of a company that scaled up well through being receptive to investor advice and other advice. So that would be really good. Each year in the CDL program, we select the best company of the year. And then CDL has 4 sessions in a year. And then there's something called the super session at the end. And the super session is the best venture in each stream. And then they all come together. And so with quantum, we pick the best one each year and they go to super session. I think this is public knowledge. It can be looked up. One of the recent ones was Dirac, D-I-R-A-Q, semiconductor-based one that came through. It's an Australian company. I was very impressed by how they performed. I think Multiverse came through. Multiverse is now a strong software-oriented company. There's a lot of examples, but the answer is everyone that made it to the super session from the CDL Quantum was an impressive venture.
Professor, would you like to share updates on your work? Because you've been working on quantum sensing, metrology, communication, and optics. Is there any research updates that you would like to share with the audience?
Well, sure. Okay. So quantum sensing is about, so there's, a sensor in principle can be perfect in the classical world, but because everything is quantum mechanical fundamentally, there are limitations to the ability to sense. And so quantum sensing is about identifying the limits and then finding ways to circumvent. So, if something has jitter because of the quantum limit, then you want to find ways to do nonlinear optics or some sort of coupling to be able to make sure that what you want to measure, the noise level, is very low. Now, quantum sensing has great successes in the past. So magnetic resonance imaging. So people go to the hospital and get a brain scan. It's essentially a quantum sensor. So there's really good examples of successful quantum sensors in the past. The future seems to be in networks of quantum sensors. So if you imagine a brain scan, imagine instead of going in one of these machines, you wear a helmet, and then the helmet has a lot of little quantum sensors that talk to each other. It could be in the future that we have very cheap, efficient ways to scan the brain instead of having to go to the hospital in this claustrophobic machine that costs a couple of $1 million and needs experts to run. And so one of the areas I work on is on quantum sensors, how to connect clocks together, how to connect magnetic sensors together and figure out where the opportunities lie for coupling sensors together to do better than what we can do classically. And it's complicated because quantum mechanics is fragile. So when you connect sensors together, the connections might only make it quantum good for a little while. And I'm working on ways to try to get past that. I'd like to make sure there's kind of a stable advantage. In quantum cryptography, so I've done some work that's well known in assessing whether quantum cryptography is safe, subject to realities and how light sources work. And recently, I'm on a project which builds quantum cryptography, so a quantum enhanced version crypto. So the idea is that we have to do things in networks. So, we generate key, but we have to hold on to key. We got to release it at the right time. And so we can prove security for quantum cryptography, but can we prove that security at as we build it in a network? There's all kinds of loopholes that happen. You see this in like blockchain world and AI world, et cetera. The blockchain, that big break, $1.2 billion theft just past couple of weeks. An example where you think everything's secure and then there's loopholes. And so it's the same in the quantum world. You think everything's secure, but there might be ways for quantum adversaries to get around it. I work on some security protocols for quantum. Quantum is a threat to blockchain. How do we get around it? And then finally, in the quantum computing land, half the work I do is quantum control. So I work out ways to make better gates and operations. At the moment, I have a lot of work going on in nuclear operations. So my student Pragati Gupta and I collaborate with Andrea Morello's group at the University of New South Wales and various others. And we had a nice paper out in Nature Physics in January where we're able to, I talked about spin and superposition. We have a high spin nucleus and it's in a silicon substrate and it's in a superposition of spinning fast one way and spinning fast the other. So, I'm spending more time with my student thinking about the ways of being able to work with nuclei. And then one last one, the other half is I've got an application for a grant. And this one, I always need to do something crazy too, because my joy comes out of being crazy, not out of being sensible. And for that one, I've got ideas on how to theoretically consistently build time travel into quantum computers. Practically, there are ways to test this. I have ideas, but the idea is to incorporate time travel. And I think I can prove that if time travel is built into a quantum computer, it won't be any advantage. So don't bother to build it. So that's the fun one, is proving time travel is useless for quantum computing.
Professor, you also vested in nanotechnology. Eric Drexler talks about a nano assembler. In the future, maybe you could manipulate atom by atom, and then possibly maybe assemble anything and everything, a 3D assembler of sorts. What are your thoughts on that?
Well, yeah, we have. It's tough. I collaborated with a group. Bob Volkoff, who's at the University of Alberta, does it's dangling bonds. So you get a silicon, and then the silicon surface is very reactive. So you passivate with hydrogen, then you yank out a hydrogen here and there, and then there's kind of this electron that can pop up in these dangling bonds and be useful as quantum computing. And so essentially you build this system by atom manipulation. And so in some sense, it's really exciting because you have this opportunity to do very fast, very low noise quantum computing. But with computers, you have to interface. So the way I think about it is when you work at a computer, you have your keyboard and your monitor, right? Your keyboard is the way to do input, and your monitor is the way to see the answer. And then the question is, if you do something at the nanoscale, atomic level, on one point, you can make these qubits and everything is really, really good. But then how do you get your keyboard to be able to send the instructions to be able to control it? This goes back to the architecture questions I mentioned earlier. And how do you make sure that you can read it in a way you see on the monitor. And so on the nano scale, we're getting better at manipulating so that in principle, we can do some really beautiful, coherent information processing at the quantum level. On the other hand, the input output is really difficult. So, and there's always this trade-off, there's always a really good way to implement. I mentioned superconducting and photon and neutral atoms and ion trap. They're not at the nanoscale, but the nanoscale holds opportunities, but there's obstacles along the way, and I don't know how to get around those.
My last question to you. Professor Seth Lloyd has written a book which says that the universe is a quantum computer. What are your thoughts on that? And maybe it will be great if you could leave us behind with the future of quantum computing. What do you think a working, practical quantum computer will do and how it will completely upend our world?
Right. Okay. Yeah. So Seth Lloyd's book is very provocative. It is the universe quantum computer. So at the beginning of our conversation, we talked about to understand a quantum computer, first understand a computer. And so my view is, as I said at the beginning, a computer is a machine. It accepts zeros and ones as input, and it delivers zeros and ones as output to solve a computational problem. Now, forget about for the moment that the universe is a quantum computer. Can the universe be a computer? Well, where's the input and output? Is the input, so you can imagine that you make a universe, and then we got fundamental constants of the universe, the speed of light, the Planck's constant of gravitation, such things, charge of an electron maybe. And so if we, actually I should say technically, charge and speed of light aren't independent, they're in the fine structure constant, but that would only be for very careful listeners. So the idea is that, what are we computing? Is it saying, I can imagine a way to compute it. Somebody who creates the universe says, okay, I'm going to try these parameters, and then I'll see if the universe develops self-aware life forms, something like that. Is that what's being computed? In Hitchhiker's Guide to the Galaxy, we know the answer is 42, but we never quite figured out what the problem is for which the answer of 42 makes sense. Now, this ultimately comes down to, if the universe is a computer, it's got to compute. And it's got to compute for somebody who is either outside the universe, who can make input and then output, but the universe is almost by definition, there's nothing outside, not even space and time. Or there has to be a way to overcome measurement problems and to say, no, inside the universe, we can compute something. But the fact that the universe is evolving some kind of quantum information, we can have a description of the universe as evolving, and quantum information concepts can be useful. And there's this whole program that used to exist in the Simons Center, Simons Foundation, which was called It from Qubit. And so, the idea that reality can emerge from some qubit description. So quantum information and quantum computing is useful to try to understand various things, even, evaporating black holes, all kinds of stuff. But I just don't see how it's well posed to talk about the universe as a computer, classical or quantum. And then you asked about the future of quantum computing. So I held a session. I was co-chair with Christa Zufel from IBM in Zurich, and I were co-chaired a conference called QTML, Quantum Techniques, Machine Learning. It was in Melbourne in late November, Melbourne, Australia. And unfortunately, the conference was timed to be during American Thanksgiving. So we had the conference in person, but almost nobody from the United States wanted to come because Thanksgiving is their big holiday. So I decided to put together a panel that was virtual. And then that virtual panel had 4 leading US quantum scientists on board. It's on YouTube, so it's look upable. And there's this famous or infamous podcast by Sabine Hossenfelder, who, me personally, I really enjoy watching her videos. And she did a video on this session I chaired in Melbourne. And the title of it was The Future of Quantum Computing. And so I'm just saying that it's interesting to go through that. And I'm writing a paper with the people involved. It was Eddie Farhi from Google and MIT, Scott Aronson, who's in Texas, Aram Harrow at MIT, and Andrew Childs at the University of Maryland. And each of them had a chance to chime in and discuss where the future lies. And so in that article I'm writing and the video that can be seen in whole on YouTube, one of the key messages that come out, of course, on a practical level, we're moving towards fault tolerance, and we might be able to deliver quantum computers at scale. But I like to joke that quantum computers, there's two problems. One is we don't know how to build it and at scale. And number two is we don't know what to do with it if we build it. And the second problem is much worse than the first. And so what we've learned, we have quantum algorithms, we have problems for which quantum computers can show advantage. Shor's algorithm is a really good example. Grover's search is another really good example of where there's provable advantage. Whether they're practically useful is very debatable, but the message that does come out is the advantage of quantum computing applies, as I said, it's not like nano, it's not speeding up everything. It's some problems would be better in a quantum computer, and these problems have some structure to them. So a quantum computer could be really good if we find problems that have a structure that's amenable to where the advantage of quantum computing comes up. So where's the future of quantum computing? Well, building a bigger quantum computer is a technicality, a very hard one. Smart people and lots of money go into it, but we don't see a reason why we can't make them big. There's no law of nature that says you can't make a big quantum computer. And if there is, that would be really interesting. But then the question is what we do with it. And that's the question of the future. What would be the problems for which a quantum computer can offer an advantage? And that's really hard. And that might take a long time to identify those problems. Lucky we have time because, quantum computers still aren't big. So we don't have a big enough one to be useful yet. And trying to figure out what problem it's good for, thank goodness we have time to do that while we wait for quantum computers to scale up. But that's the future of quantum computing is what the heck is this big quantum computer? Cryptography.
Right. Professor, thank you so much for taking time and being part of the podcast. It was truly insightful. I'm going to definitely add the YouTube link that you spoke about. Wish you the very best. And I hope we get to a useful quantum computer. And I hope in the meantime, we also kind of understand what we can do with it. So thank you once again for taking time and being part of the podcast. And to my listeners, if you like what you see in here, then please press the subscribe button. And until next time, see you guys. Thank you, Professor. Thank you.
Thank you very much.